One of the important aspects of dealing with real fluids and their thermodynamic properties is to understand the equations of state. The most familiar equation of state that we have is the ideal gas law. It's not an equation of state, it is a law. And the ideal gas law is offering a linear relationship between the temperature of a fluid and P times V. At constant temperature, P is inversely proportional to V. And this state is an approximation of what we really have. And let's look at this problem from the diagrams on the board. Now here we have a pH diagram. Here we have a PV diagram. And on the PV diagram, the ideal gas state is way above the critical point, and we have an inversely proportional relationship between the pressure and the specific volume of the fluid. And this relationship is universal. It doesn't matter whether you have nitrogen, oxygen, methane, water, or anything else. It behaves the same. It is not fluid specific. But there are certain limitations of the ideal gas law, and let us iterate its assumptions and limitations, and let us remove those assumptions one by one. The first of the assumptions is that this volume belongs to the volume of the void, and the volume of the molecules are not taken into consideration. So, volume of the molecules are neglected in the ideal gas law. So this is the first assumption of the ideal gas law. The second assumption of the ideal gas law is that the molecules do not interact. Under these circumstances, the equation is on the board. Let us remove those assumptions and let us arrive at an general equation of state, which is going to guide us in understanding the behavior of the real fluids. But first, let's establish the necessity for trying to find an equation of state as such. Now, when we look at the PV diagram of a real fluid, we see that, unlike ideal gas, the real fluid has a singularity at the vapor-liquid transition, that we have the same pressure, same temperature, but two different volumes that is needed to describe the behavior of the fluid. This volume corresponds to the specific volume of the liquid. This volume corresponds to the specific volume of the vapor in equilibrium with that liquid. So that singularity that we observed in the vapor-liquid equilibrium is mathematically inaccessible for a relationship like an ideal gas law. The relationship is only reciprocal, and that reciprocal relationship has a graphical behavior like this. It is not accessible through a quadratic equation, because quadratic equation is symmetric. But cubic equations represent the singularity very well, because they have a behavior that in its continuity may look like this. So this is a cubic equation that allows us to estimate two roots of the vapor-liquid equilibrium, that allows us estimate the liquid volume, that allows us estimate the gas volume as it approaches to the ideal gas state. So we are in the search of a cubic equation. Let's remove the assumptions of the ideal gas law. Let's find our cubic equation of state and then iterate on that cubic equation of state for further analysis of the real fluid behavior. Now I'm going to remove the volume of the molecules assumption first. So here my pressure expressed in terms of RT over V represents volume of the voids. If that PVT relationship belongs to volume of voids only, and if that volume is the total volume, I have to subtract the volume of the molecules, so that what I'm calculating with this equation, through this equation, is going to be more accurate. This being done, I have to remove the assumption of non-interacting molecules. I know that when I start compressing a gas, when molecules move closer together, their attractive and repulsive fields will be accessible through each other. And those attractive fields can induce a pressure that is lower than the pressure, can induce a sensed pressure at the molecule site that is lower than the external pressure. So I'm going to subtract for the attractive forces. And the fact that I need two molecules to attract one another requires a concentration square equivalent of representation. So I have V square here. So with this reasoning, I have a cubic equation of state. This one is the van der Waals equation of state. Van der Waals. I'm going to refer to this equation of state with the acronym VDW. Let's see how cubic this equation of state, how it becomes a cubic equation of state. So I'm going to balance the denominators. So I have RT V square minus A V minus B divided by V minus B times V square. So as you can see, through the denominator, I have a V cube minus V square B. I have V square terms, V terms, and V independent terms. I have a cubic equation in terms of volume. So if I keep the temperature constant, and if I plot pressure as a function of volume, I should have a cubic equation behavior. Now this cubic equation behavior is not consistent with my expected fluid behavior. My expected fluid behavior is I expand the liquid until it has its saturation temperature, saturation pressure at that temperature, and then my liquid evaporates or boils until all of it is in the vapor state, and then my vapor expands. So it has to follow a straight line, but this cubic equation doesn't follow that actually. It follows a different curve. Careful experimentation has demonstrated that this cubic behavior is meaningful actually, because when we were carefully doing this expansion, slowly, carefully, isothermally, experimenters have discovered that it is possible to go beyond the saturation line and have a state which we call the metastable state. On this side, we have a metastable liquid. On that side, we have metastable vapor. metastable means that you may maintain its stability, but it is not at the perfect equilibrium, right? So our stability terminology now has metastability in addition to the stability and instability. So in this metastable state, the fluid behavior is consistent with what thermodynamic dictates. What does thermodynamic dictate? Real life observation also, of course. The rate of change of pressure with respect to volume at constant temperature should be negative, right? Rate of change of pressure with respect to volume should be negative. If I increase the volume, my pressure should decrease. If I increase the pressure, my volume should decrease. So in the domains that I have labeled as metastable liquid, this condition is valid. But in between the domains that I marked with red, all right, I have an unstable fluid where increasing pressure increases volume. So we know that fluids do not exist in this state. If we force a fluid to exist in this state, the fluid breaks down into its stable, liquid, and vapor fragments. But it is possible to remain in these metastable domains. And those metastable domains, if accessible, they can be technologically very useful, very important. How so? Now, metastable materials are at our disposal. Nanomaterials are metastable. Nanoparticles of catalysts are metastable. We may have fluids in the metastable vapor state which are at a lower temperature but still a vapor. We may maintain them as a vapor at that lower temperature, and immediately after they reach this unstable region, they will collapse and condense and become a liquid. But using this as a vapor, we can carry out separations. We can just have extraction processes based on those metastable vapors. Mist is a metastable vapor. Fog is a metastable vapor. So there are very useful technological and everyday applications of those metastable states. In addition to the fact that they are also a thermodynamic curiosity and a good intellectual challenge. Now, we have also learned about the stability condition, that our volume should decrease as we increase pressure, as our volume increase, as our pressure increases, our volume should decrease. This is the stability condition. We now understand the need for a cubic equation of state to express the vapor-liquid transition behavior very well. We can now proceed with further understanding of the fluid behavior through more accurate representations of these equations of state. This van der Waals equation of state sets the basis of all those equations of states, but we have a couple of more equations of states which I will transfer to the board for future reference, which are very much in use in expressing a fluid phase behavior. Two most commonly used equations of state in representing the physical behavior of the real fluids is Pengen-Robinson equation of state. It has proven accuracy, especially in predicting the behavior of mixtures, vapor-liquid behavior of mixtures, and also the virial equation of state. Now, one thing in common in both of those equations of state is that we have the constants, parameters, are functions of temperature. This parameter, if you remember, was representing the molecular interaction, attractive repulsive interaction parameter, and setting a temperature dependent value for this is going to increase the accuracy of the predictions, as well as the parameters of the virial equation of state. Now, given those three equations of states, Van der Waals equation of state, Pengen-Robinson equation of state, and virial equation of state, it might be useful to also represent, to obtain the Van der Waals equation of state constants A and B in terms of the critical point parameters. This goes through the stability criteria and the conditions of extremum of a cubic equation. So the conditions of extremum of a cubic equation goes as such at the point of extremums, at the point of maxima and minima, del P over del V at constant T should be 0 at the extrema. Extrema corresponds to maximum, minimum, and also to the saddle point. Now, the maximum point of this fluid, of this curve, is here. Minimum point is here. And we also have a saddle point, switching from concave to convex behavior in the continuous curve. This extremum of the second derivative, the saddle point requires a second derivative to be equal to 0 also, along with the maximum behavior. So when we take these concepts and apply it to the Van der Waals equation of state, we have del P over del V at constant T to be equal to 0 when temperature is the critical temperature, and its second derivative is also equal to 0. From here, we obtain two equations. All right? We take the first derivative, we have one equation. We take the second derivative, we have the second equation. And the constants of these are that A is equal to 9 V sub c RT sub c divided by 8. B is equal to V sub c divided by 3. And perform this exercise. It's useful, it's instructive to obtain these constants from Van der Waals equation of state. But be careful, those A's and B's are only valid for Van der Waals equation of state. With those A's and B's, Van der Waals equation of state has a compressibility factor at the critical point to be a process constant, irrespective of the fluid. The critical compressibility factor for Van der Waals equation of state is constant irrespective of the fluid. That is where the predictions of the Van der Waals equation of state weakens. That's why we need more complex equations of state, such as Penn-Robinson equation of state or virial equations of state, we have temperature dependencies of the constants as well.